Okay, so good morning, and today we begin a new topic, and so uh, the study of the dynamics of rigid bodies. So we'll spend a couple of lectures doing various things. Okay, so oh no, what is going on? Okay, I thought I'd fix that. Okay, so first question to the class is how many degrees of freedom does a rigid body have? How many?
6.
We discussed this. Okay, 6. Answer is 6.
3 3n minus
Yes.
k, where k is the number of constraints.
No, wrong. So then, yeah, I mean, the k, once you put that in, it is 6. K is 3n minus 6 for a rigid. That's what we had discussed for n greater than some number. Okay, so the answer is 6. So the key point is that one can be clever in choosing these 6 coordinates. Okay, and we will do it as follows. We will do it by in terms of a vector y and a bunch of angles, some theta, psi, and phi. Okay, so this is a vector. So 3 plus 3 6. So this is we will choose. Will be chosen. We'll discover that we have something like this, and this will be the center of mass. And these 3 will be some angles. Usually there's a term for this. These are called Euler angles. But I mean, and this are related to the orientation of the rigid body. Okay, many of you may have seen these choices already, but I want to tell you why. So even if you've seen this, goal is to motivate why this choice is good. Okay, given that we know some advanced dynamics, and we will just do that. So we'll model. So our model for the rigid body, which it's not the most general rigid body. So we have say n particles or masses, Ma located at some point x. Okay, so this is our model, and of course, xa minus xb is fixed for all a and b. Okay, so this is a rigid body, right? All the distances and I mean these things are fixed. Okay, so I should say mod, right? It's fixed. Okay, so but if we don't put in this constraint or whatever, I mean, we have to put in these constraints. We will put it later, but for the moment, we will ask what is the kinetic energy. Okay, it's very simple. Okay, we'll use an index A, right? A goes from 1 to n. I won't keep writing that. There are n masses. MA, okay, vector XA dot square. And uh, this is the kinetic energy for this. Is this clear? So nothing. Okay. So for instance, if even if it were not ideal, it's not a rigid body. It could be n particles in a rigid gas, in an ideal gas. Again, this thing would still work. Okay. So this is nothing deep. But I mean, now we're going to motivate the following thing. Consider a new coordinate. Okay. New set of coordinates. New. For each n, we will do this. Okay, is this clear? This is just some. This is just some quantity, some vector. At this point, it's just the same vector. Okay, it's just a vector worth. And we will choose y in a. We'll use this. So we will use this freedom in choosing y. I mean appropriately, and we have to see what that is. Okay. So now what the idea is that we want to write. So this implies that xa is ya plus capital Y. So we can plug it into the kinetic energy and try to write it in terms of this guys. So T would be half sum over A MA XA dot square. So that would be YA dot plus Y dot whole square. Okay, we can just expand this term. Okay, so this is nothing. I'm just expanding this thing. Okay, so any questions to this point?
Sir, there is a
Won't
half
there
in
be a
next line.
half in the last term?
Yeah. Anything else? I forgot a dot here, which I put it. Okay. Anything else? Okay. So now the point here is that if we were able to do something, so I'll just say that what we want to do, and then we'll take it from there. Okay. So let's do this. Okay. Suppose consider this term. Okay. Suppose we can choose y, okay, such that this term vanishes. Then we see something interesting. This t becomes then t is just sum of two tuples. Okay. So what we see is that the y variable, y degree of freedom separates nicely, right? So it decouples from the little y's. Okay, so we see that. Okay, y decouples from the little y. Is this point clear? Okay, so let's just go ahead and ask how we can achieve it. Okay, so what we will do is okay. So what is the choice that we need to do? So that term is just so what we want really is should be 0. Okay, we will do something stronger. So let's do that.
Sir, it could be any constant, right? Not necessarily 0.
Yeah, but I want it to be 0. I'll do. Yeah, you're right. Absolutely right. Okay, we will choose to obtain something stronger. To set actually, we'll choose something stronger. Okay, that is. I have to put some vector in some place. Okay, so let's ask how whether this condition, what this condition implies. Okay, so what is ya? So this implies which is the definition of ya, right? We subtracted some constant vector. Okay, 0 equal to this. Or y equal to okay, and so this is the okay. So this is the reason. So this is the center of mass coordinate. Right? Vector or coordinate. Is this clear? That this is achieved if we do this. Any comments and questions? Okay. And so let's make so let's look at the part of t due to y, and let me define capital M to be summation AMA. Okay, so the KE term for y is then half M y dot square. Okay, and so is this clear? So this is like or similar to the kinetic energy of a mass m, capital M, okay, with coordinate vector coordinate y, right? This is what that's what it looks like. So, and it completely decouples from the y's. Okay, so that is that takes care of the choice of why we chose y. Okay, is this clear? Somebody please answer if it is clear. No, why we have chosen this? We want the cross term to go.
Yes, sir.
Is it clear? Okay.
Sir,
very
the
good.
stronger condition being summation MAYA equals to 0.
Yeah.
It's just that if this is 0, its derivative will be 0. So
Yeah.
Okay.
It's stronger, right? I mean,
Yeah.
as somebody pointed out, I don't even need even summation MAYA, this thing. No, not this. What is this equation? Yeah. In fact, this equation itself is stronger. I mean, I could have put a constant. Okay. But, okay. So now, so the idea is now so far we have not used the fact that it's a rigid body and various things are, so let's, so now let's, let us,
I have one doubt.
Yeah, go ahead.
Initially, the kinetic energy was just summation MA XA dot squared.
Yeah.
We were the ones who introduced this small y, and then we decoupled it. So
Yeah.
So far, like, what is the use of this?
Yeah.
small
So
y?
the small y is going to, from that we have to extract 3 more degrees of freedom, and I'm going to show you how. Okay. So it looks, at this point, it looks like, 3n minus 3 degrees of freedom, but that's not correct. I mean, there should be only 3 coming from that, because y is satisfy this constraint. MAYA is 0, that's 3 constraints. There are 3n numbers, so 3n minus 3. So, okay, so now we will, let us try to extract the other 3 degrees of freedom. From the y's. Okay, so that's what I want to do. Okay, so for that, what we will do is we will choose, let us choose an orthonormal basis or frame, okay, which I'll write as E1 prime, E2 prime, and E3 prime. Okay, that is the located local basis at the point y. Okay, so the picture I have in mind is the following. So I have a lab frame or some body, I mean fixed frame. Okay, this is the origin. And then what I do, move this point a bit. I pick another point O prime such that, okay, so let's do something. Very nice. Okay. This is the vector y. So O prime O, okay, is the O prime, and so this is a vector. Y. Is this clear? So that's what we have. And what we are going to do is at this point we will choose something which is kind of, what you should imagine is that there's this rigid body and O is some point on it. It may not be a point on it, but a mythical point in that thing where we have, we have this a different basis. Okay, so this is the at the point Y, and it is tied down, or the rigid body. Is this point clear? So this is what we are doing, and what I'm going to do now. Why? So the thing is that we will write YA in such that O prime is the origin, and then we can just go ahead and expand these guys, YA, as follows. Okay, so these are the coordinates in a frame located at O prime. Okay, so this is some fixed frame. Okay. So is this clear? Is this definition of the choice of YA clear? Okay, and this is sometimes called the body frame. Okay, so once we do this thing, we can now work out what Y. Okay, so the most important point here is these guys are fixed numbers. They cannot change.
Sir, YA with respect to the body frame only?
Yeah, it's only in the body frame. Yeah. Yeah, that's why they are fixed numbers. What I did it for you. Okay, so now we can work out something which we know, which we are using, which we have done already. Okay, there is no Y dot AI because those are zero. They don't change because they are just a property of the rigid body. Is this clear? So there is no one. There's only one thing, and this frame can change. So this we will call, and this we can use what we did earlier. We can define angular velocity this way. So this will be 1AI times omega cross. Is this clear what I have done? So this is the angular velocity of the frame, but we will call it angular velocity of the frame of the rigid body, because it's tied down to the. If you called it frame, it's okay, but I'm just saying this is something which is. Okay, so this is what it is. So now let us look at.
So there is no way the number of degrees of freedom are going to change, even if we manipulate the frame we are choosing.
Yeah.
So
you just wait. So we will. I mean, I haven't told you at this point. We are just doing some calculations. So we will see how the 3 degrees of freedom emerge in a moment. Okay. Right now we are doing some manipulations, just defining things. Is that clear? Okay. Yes. So I'll give you the short answer. It is just the 3 degrees of freedom is the arbitrariness in choosing E prime in, say, with respect to the body frame. So there'll be some rotation matrix, and that rotation matrix will have 3. We know a rotation matrix in 3 dimensions. RB has 3 parameters. So those are the 3 parameters. Those will be some angles. That's all. Okay. So let's just do this. So now we can write t. Okay, using this, we can write t as follows. Plus, of course, the other two. Okay, so all I've done is substituted for dya by dt into this thing. This is what I've got. This I want to simplify a bit, the first term. So we'll do some algebra. We need to work out what this is what we need to work out. Okay, so let's do this. So this we can write as epsilon I j k omega j y a k. Second term is epsilon I L m omega L y a. Okay, so if we do this, then we can use epsilon. Epsilon is delta delta, so I can write that as delta JL delta Kn minus exchange Jm delta Kl times omega j yak omega L yan. Okay, so this, if you work out, so delta JL, this would be omega square times ya square minus okay, so we have worked out this identity, and so let's go ahead and plug it in here into this thing. So using this result in T, we get the following. Okay, and so this particular term can be rewritten in an interesting way. So this can be written as follows: is equal to half omega I j, repeated index is summed over omega j where okay, so the key point here is, the key observation is that all dependence on ya has been absorbed in Iij, in this quantity Iij. Okay, is this clear? So now we have seen is that what we are seeing here is that all the YAs should disappear. Okay, and there is just this omega, which is the property of the frame, which is remaining, but that's about it. Okay, so this Iij has a name. What is it called? Anybody?
Moment of inertia tensor.
Yeah. Okay, and so now the thing is that usually we don't think of a rigid body. Usually we think of it as a continuum. Okay, so we can write a continuum version. Where we replace, summation AMA by some dV rho density, mass density. Okay, so then there is a volume of this thing. So then Iij in such cases will be integral over the volume of the rigid body. V is volume of the rigid body, dV rho of y. Okay, so let's write some properties. First one is it is a symmetric second rank tensor. Symmetric means Iij is equal to Ij. Very easy to see because you see here delta Ij is symmetric, so is Yij. So it's obviously symmetric either here or in the discrete form. Okay. So there's a second way of writing it. You can think of Ij can be represented by a 3 by 3 matrix. Which write as I11 or Ixx. I11, I12, I13, and I21 you would write, but that's the same as I21. I23. This will be I32, which is the same as I31, which is the same as I13. I'm just writing only the I23, I33. So you can see that the independent guys are these 6. Okay. The rest, other 3 are determined by this, right? Because it's a symmetric thing. And then you can, okay, and we can do the following. We can write omega to be this vector omega 1, omega 2, omega 3, and then T, where we can write it as transpose of this. So omega 1, omega 2, omega 3, and the matrix Iij times half of this. Plus, of course, half M. Okay, so the last property, okay, which is there exists a rotation. That's that Iij, okay, can be made diagonal. So let's first write how the second rank tensor transforms. So I prime, this would be I1, J1, R is some rotation matrix, I2, J2, I, J1, J2. Repeated indices somehow. Okay, so so there exists R such that I prime is in the matrix here, which is I prime 1, 1. Okay, this is just a simple statement that a symmetric matrix can be diagonalized. Okay, so is this clear? So what we have done is we started out with what looked like many coordinates, and we have just brought it down. And so the data we have, data for the rigid body, is as follows. It's the coordinate y and a frame, orthonormal basis. Okay, so now, so the thing is, how do we explicitly show the 3 degrees of freedom? Okay, so what we have, and this could be in general a function of t. Okay, I'm just for completeness, I'm writing it. And this should be equal to summation j equal to 1 to 3 e hat I, which is a fixed basis. This is a body basis, right? Times rotation matrix, which could have the time dependence. Right? So this okay, so this is an orthogonal matrix, so it has only 3. Okay, so of course R transpose is identity, and determinant of R is what? Plus 1. So comes down, how can we parameterize R? Okay, so I'll give you one, which is as follows. We have seen this. Any arbitrary rotation matrix can be written as a rotation by some angle theta with some axis t. And then you can show that this can be written as exponential of theta times n is some unit vector, times a triplet of matrices, okay, antisymmetric matrices, for which we choose a basis T1 Okay, so this looks very complicated, but actually I can write it like this: di of jk is the Levi-Curie data. Okay, easy to prove. Okay, so now where is the time dependence? So where is the time? So R depends on time, and where should the time dependence come from? Where can it come from? Anybody? Any ideas how we could put time dependence in the story?
Theta.
Theta, only theta? Even n can change. Okay, so we can, so that's correct. Theta also, that's correct. So we can, let's say, just for simplicity, I'll define some vector n of t, which is theta of t hence n hat of t. Okay, so this is three variables, three numbers. Okay, so what we will do now is this is not the standard, this is not the parameterization, this is nice group theory things. So group theoretic stuff, but here, okay, we'll choose a second method, which are called Euler angles. Okay, and here what you do is you do a sequence of 3 rotations. Okay, and so let me write that out. So first you start with R. It's a rotation about the z-axis with an angle phi. Then, okay, I do it right from left. Then I do a rotation over the x-axis, theta. And the last one is back to z rotation, but now by an angle psi. Okay, so this is the general rotation matrix that we consider. So you can see there are 3 parameters: psi, theta, and phi. Is this clear? Okay, but now you might think, oh, this is great, but this is there are other conventions. So this is what we will call the X convention. So there are books which replace this with Y. That's the Y convention. So you have to be careful. So in this course, we are choosing the X convention. Is this clear? So these are the phi, theta, and psi are the Euler angles whenever I say that. Okay. Okay. So exercises now for you. Several exercises. We'll go back to white color. One second. Whole bunch of exercises. Most probably they will all come in your thing. The first exercise is multiply. By the way, all of you know this is strange. I thought I had switched off finger drawing. Okay. So multiply the 3 matrices. To obtain the single 3 by 3 matrix. And all of you know okay, so a quick question. All of you know explicit matrices, right? We have worked out this earlier in this course, right? We know how to write general matrices for rotations about x-axis, rotations about z-axis and y-axis. These are easier. Okay, so this is the thing. The second second exercise is, now that we have this thing, so we have got a matrix R. So we know that EI prime is equal to summation J EJ times RJI, sorry. Okay, so this is what we have. So now, taking derivatives, so by computing dE hat by dI prime, express omega in terms of phi dot, theta dot, psi dot phi theta and psi. Okay, so let's do this. I'll give you the answer. Okay, and finally what you can do is, yeah, so then third one is express t in terms of the degrees of freedom psi theta phi, and their derivatives, of course. So please, this is just straightforward exercise, so you can do it. Okay. So I think I'll stop here. How much time? Oh, I still have about a minute or two. So I just do some. We can the following computation, which I'll show. So we already know this. Okay. We also know that this is equal to omega cross. This is the definition of omega. So by looking through this, we should be able to do this thing. So what we will do here is insert R inverse out here. I know R inverse is R transpose. You can do that. And then what we will get, this implies that omega equal to so I have to explain a little bit. What this means here is that you take the matrix, the dr by dt means you take the matrix R and each entry you differentiate it with respect to time. R inverse is just the transpose of that matrix. You multiply them and do this thing. So what I've done is put an R here. So Rej will give you again Ej prime. So I want to go back to the prime variables. Okay, so this is what we get. And so we can take this guy. So this is we get from here. And then we can dot it. Do the following. E j dot. We do that. So we'll pick out that guy. Dot with this. So what we get is LHS. Okay, we can use the cyclic property of this. This is equal to omega dot ei prime cross ej prime. So this is what we will get. And so we can just go ahead and now this will be equal to R inverse dot dr by dt, the jith component. So for instance, example, we can ask, so we can, if we took I equals, so let's say we take I equal to 1 and j equal to 2. Okay, so that will give you, from here you will get E1 cross E2 is E3, so that will give you omega 3. That will be equal to R inverse dr by dt ji, which is the 2-1 component of this matrix. Similarly, okay, if you take I equal to 3, j equal to 1, that will give you omega 2, and I equal to 2, j equal to 3 will give you omega 1. Okay, that's it. Okay, so I'll make a claim. R inverse dr by dt is an antisymmetric matrix. Can you prove it? Okay, hint. R can always be written as e power some antisymmetric matrix. So I'll stop here. But what we can see is that conventionally we don't have to do these fancy things. We just do simple things. We compute stuff and get this. We can express t, etc. And this will be the starting point of our next lecture, where we will. So what we have done so far is only worked out the kinetic energy term associated with that of a rigid body, and it gave us special choice of coordinates called the center of mass, and then we got the Euler angles. Okay, so that's all we have done. Today's lecture was only telling you why we are choosing these particular sets of coordinates. Okay, so I'll stop here and pause for questions.
Sir, when we multiplied the 3 rotation matrices, in the first one, the subscript of E cap was Z. So should it be Y or?
No. Z, X, Z. Okay. See, the thing is that after every rotation, so first we did a rotation about the Z axis. Okay, see, they don't commute, you see. The third rotation is also about the Z, but it's about a new Z axis. So it's nothing related to the original Z axis. It's not equal to, okay.
Okay, sir. Okay.
That is the reason. They don't commute. In between, there is something which doesn't commute. I mean, 2 rotations about the Z axis will give you, they'll join and they'll add up. But after you do a rotation by phi about the Z axis, then you're doing a rotation by theta about the new X axis, whatever is that. And then you're doing a rotation about by psi about the new Z axis. So okay. So that's what is going on.
Okay, sir.
Good question. Anything else? Let's stop recording.